Hello, welcome to today's A-level physics lesson. In today's A-level lesson, we shall be considering CT scan. CT scan is a device that gives a better and detailed result compared to X-ray scans, and it is a more sophisticated device because it involves more exposure of an object to radiation or X-ray. Based on our A-level syllabus, we shall be limiting this lesson to what CT scan is all about, to the differences between CT scan and conventional X-ray. We will also be considering key components of CT imaging. We will likewise be looking at other unique things about CT scans. Then we will be looking also at the development or construction of image using CT scanning. Then lastly, we will be looking at the principles behind CT scanning, the principles of CT scannings. So we shall be looking at what is CT scans. Well, CT scan, also known as computer tomography, is an imaging device which make use of computer processed combinations of many X-ray measurements taken from different angles to produce cross-sectional images, which is also referred to as visual slice of specific area of a scanned object, allowing the user to see the inner structure of the object without cutting. This is what makes a CT scan a bit more sophisticated than X-ray scan, because the CT scan make use of a computer process combinations of many X-ray measurements, unlike X-ray device that is only used to take a measurement of an object or to diagnose a body just in one direction, or just to get a image of such a body, and that is far different from what CT scan can do. Apart from that, based on the definition, the CT scan as well helps in taking measurement from different angles, which is not obtainable in X-ray scan. And again, it produces cross-sectional areas or visual slice or specific area of a scanned object, and this is the wow part of the CT scan, because it can give the detail of an inner structure of a body. It gives the whole cross-sectional area of the image of a given body that is being diagnosed, which is not possible in X-ray scan. Okay, so from here we shall be considering the differences between CT scan and X-ray scan. But meanwhile, we also want to add this, that the CT scan is formerly known, or was formerly known rather, as computerized X-ray tomography. which is also referred to as CAT. That was the initial name of CT scan, but now called computed tomography. So let's quickly look at the differences between the CT scan and the conventional X-ray device. One of the differences between the CT scan and conventional X-ray is the fact that for CT scan, many images of a slice or section through a body is formed at different angles. Is formed at different angles. The implication of that is that we can obtain as many as possible images of a particular section or slice of a body. All we just need to do is to operate the CT scanner in such a way that it takes measurement from different angles, and this is just automated. It's fully automated, meaning that the CT scan can actually do that on its own. Okay, so what the operator is just meant to do is to finish up the result that comes from this device. So many images of a section through the body or a body is formed at different angles. So I can have an image of a particular area of the body number of times just from one shot from a CT scan. Now the images formed is built up to form a single image, just an image, to form an image of a slice. So for many images of a given section, we can form a single image just by combining those images together. Now, if we are not considering many sections of such a body, then what we need to do is to combine the image of each section, the image already formed from each section, we'll combine it together to give us a 3D image. So meaning that a 3D image can actually be developed by combining the image of each slice. And 3D simply means three-dimensional image. Okay, so I think that that is noted already, that many images of a slide will give us a 3D image if combined together and developed. But for X-ray, only shadow or flat or 2D image can be obtained. We can only obtain a shadow, flat, or 2D image. Okay, and this has nothing to do with the depth of the body. It has nothing to do. So regardless of the depth of the body, X-ray will always give a shadow, flat, or 2D image. And that's what can be seen from the picture right there. You will see the first one, it's very sharp, detailed, bright. But the second one, just look at it, looks like the shadow of the skull of a human being. Okay, it's not sharp enough, it's not well detailed. But from the first one, I can see the oster, I can see the thing, I can see virtually every part very clearly. Okay, so This is the obvious difference between the CT scan and the conventional X-ray. Okay, so from this very first point, you can earn as much as 4 to 5 marks in your exam if you are asked to state the difference between a CT scan and an X-ray. Sometimes A-level, Cambridge usually award 5 marks for such a question or 4 marks for such a question. So irrespective of that, just mentioning this first point alone earns you your 4 or 5 marks. Meanwhile, there are other difference between the CT scan and the conventional X-ray. Number 2, for CT scan, 3D image formed from slice produced can be rotated. That is one of the unique feature of a CT scan. The 3D image formed can be rotated or viewed from any angle. Okay, so when observing the result or when looking at the result formed, which is a 3D image, I can rotate the result at any angle to observe it. But that is not possible in X-ray image, because X-ray image cannot be rotated since it is a 2D image, two-dimensional image. Now, one of the reasons why we have many images formed from a CT scan before finally yielding a 3D image is because the CT scan involve a greater exposure of a body to X-ray beam, while X-ray image involve a single exposure. Okay, so that alone distinguish the potency of each of these scanners. Okay, the CT scan can give a 3D image since it can produce many images which is finally combined together. Okay, and that's as a result of a greater exposure of the body to X-ray beam. Why X-ray image involve a single exposure? Okay, right from here we shall be considering key components of CT imaging. What are the key components, the key part of a CT imaging or CT device or scanner? One of the components of CT imaging is X-ray tube. X-ray tube. The X-ray tube projects fan-shaped X-ray beam in many focal spot position to produce many views. That's one of the unique things about this component of the CT imaging. The SA tube projects fan-shaped X-ray beam. Okay, it projects it in many focal spot position. So meaning that the X-ray beam coming from the X-ray tube does not stay redundant or is not just focused at one direction. It simply means as the device is being operated, the X-ray tube move from one spot to another spot. Okay, so its direction keeps changing over time as it takes the image of the object, and that is done by projecting an X-ray beam, okay, to produce many views from different position or many position. So that's one key component. Another component is detectors. The detectors record data obtained from each view as slice in a data set. I take it again. The detectors record data obtained from each view as slice or section in a data set. Okay, so this simply means that the detector only takes a reading, okay, of the uh, X-ray beam that is being incidented on the object, on a given spot or a given section or slice of the object. So the detector major work is just to take a record of data from each view, okay, upon where the X-ray tube is directed to, and upon where the X-ray beam is incidented upon. Let's quickly see a diagram to show this. Here I have a diagram, a skeletal diagram, to show the inner structure of a CT imaging. Here is the X-ray tube, and here I have the detector, the X-ray detector. Here I have the X-ray beam coming from the X-ray tube. Here I have collimator. The collimator work is just to regulate the degree or the strength of the X-ray beam coming from the X-ray tube, or rather the intensity of the X-ray beam. Okay, so that will call it collimator. Okay, the Y here is just the object to be measured. And another thing is that the X-ray tube and the detector, okay, move at the same time and in the same direction, okay, at a particular given angle. Okay, so when the X-ray tube moves in this particular direction, that is a clockwise direction, the detector also move in a clockwise direction by the same angle to which the X-ray tube moves from its initial position. Okay, another important thing to know is that this beam coming from the X-ray, coming from the X-ray tube, okay, is going to land on the object at a particular area. It's not all the area of the object, but at a given section of the object. Okay, now the detector will now take the data of the image of that particular section and record it. Okay, so it will record the reading or the data of the section or slice upon which the X-ray beam is incidented upon. Now this particular slice or section is usually taken as a cube-like shape object. Okay, so the section of every single body of an object, okay, is taken or related or likened to a cube-like shape object, just like this. Okay, so it's related to this. So whenever you see an object of this kind, then this is actually referred to as a section, of an object. So this is a section. Okay, sorry for that. Okay, so a section, or you call it a slice, okay, of uh, the object that is being diagnosed. So this is what we use to represent a slice or a section. Okay, apart from what we have looked so far, the two components we have considered, there is another unique component of a CT imaging, and that is computer. I said it when I was defining CT scan, that it is a device, okay, that is computer processed, meaning that it is being managed, regulated, or controlled by a computer. Even the final result obtained is being developed by a computer. So computer is one of the key components of a CT imaging. Okay, and the computer work is to construct the image formed, okay, the image formed from the CT scan. So it's majorly used to develop or to construct image, okay, that is formed from a CT scan. Okay, I need you to note this, that the motion of the X-ray beam relative to the motion of the body, the object in the CT scan, is controlled by what we call the pitch factor. Pitch factor. Okay, I'm going to write that out so that I don't get it confused. Let me put it down here. Pitch. Just like a football pitch. Just something like that. Okay, so pitch factor. Okay, so that is it. So it's controlled by pitch factor. The movement of the X-ray beam, the movement of this X-ray beam, okay, and the object, because as the X-ray tube move, of course the direction of the X-ray beam also will change as well, relative to the direction of the object, because the object will keep moving into the CT scanner, okay, while the CT scan, okay, the X-ray beam changes direction in clockwise direction as the object moves into the CT scan. Okay, so that is why I said the motion of the X-ray beam to that of the motion of the object is controlled by pitch factor, or we can also call it pitch value, which is determined solely by the operator. So the operator would tell if the object should move faster into the CT scanner or slower, okay, and everything basically depends on the pitch factor of value used in controlling the CT scanner. Now the pitch factor is the distance the body is moved during one beam rotation, expressed as multiples of the X-ray beam. I take that again, expressed as multiples of the X-ray beam width or thickness. So mathematically, from there I can say pitch, just from the definition I just gave now, pitch or pitch factor equals distance of body. Okay, so I'm going to use D to represent that. I'm using D to represent distance of body per revolution, that is per rotation, then divided by beam width. So I'm going to use W for that, beam width. Okay, so that is the mathematical relationship between the pitch factor, the distance of body per rotation or revolution, and the beam width or thickness the beam thickness, okay, or the thickness of the beam. All right, from here we shall take a look at other important aspects of this topic. So from here we want to look at other unique things about CT scans. What are the other unique things about CT scans? Number one, apart from what I've said earlier on, in CT scans, measurement can be made about the body's axis. Okay, so meaning that in CT scan, measurement is not restricted to any area or to any part of the body. It can take the measurement round about the body axis, okay, from the front to the back, every side. So it can take just around the body axis, okay, which is not possible in X-ray. Another thing is that, another unique thing, each section or slice through the body is divided up into Voxels. Okay, so I've showed you what a slice mean and what a slice stands for. Okay, I use a cube to represent a slice or section of a body the other time. Okay, so when the section is divided up, then what we're going to get from there is simply a Voxel. So we can have as many as possible Voxel inside or from a given section or slice. So for every section, for every single section or slice, we are going to be having Voxels, okay, if we divide the sections. Okay, so that's one of the key things I needed to know. But the question is, what is even a Voxel, or what are Voxels all about? So let's quickly take a look at Voxels. Well, the description of Voxel is very simple. Voxels are series of small cubic units of a slice or section when the slice is divided into matrix. Okay, I've said that earlier on, that is when we divide a section, that's when we can have Voxels. Okay, now Voxels are not simply series of small cubic units, meaning that when we divide a section, obviously we are still going to have some cubic shape, but those cubic shape will not be as large as the whole body, so they are referred to as small cubic unit of a section when divided into matrix. Okay, that's from a mathematics. We have 4 by 4 matrix, we have 8, in fact standard 8 to 8 by 8, we have 2 by 2, we have 2 by 4, okay, kind of matrix. But for the sake of our topic, we'll only be considering 4 by 4 matrix kind of Voxel. Okay, so when we divide our section to Voxel, definitely we are doing that in a matrix like way to give us a 4 by 4 matrix. So obviously I will be having 4 Voxels in a section. That's the implication of that. That will be having a 4 Voxel. Okay, if you are still finding it relatively difficult to align yourself to what a Voxel looks like, okay, I will want you to imagine a set of passports. When you take a shot, you want to make a passport, and they put everything just on a roll of paper, okay, I mean of photo paper. You will notice that there you can have about 8 passports on the same photo paper, okay, not until when they cut it off into smaller sizes for you. Okay, so the same thing goes to Voxel. Okay, the whole photo paper is more or less like your section. By the time you begin to cut that paper into smaller sizes of the passport, then what you are simply doing is that you are getting your Voxel from the section. Okay, so liken your Voxel to a set of passport on a slice. Okay, a brief description of a Voxel, I mean, using a diagram is what we have here. You can see the diagram. This explains everything. You will notice that the section that I showed you has now been divided. So I have 1, then I have 2, but that yields me what? 4 matrices. Okay, I have 1 2 3 4. So this is 4 by 4 matrix. This is 4 by 4 matrix. Okay, so we are not considering it, that they just the top. Okay, so we are considering the surface here. Okay, so this 4 by 4 matrix. Now, one important fact you need to know is that the larger the number of Voxels, the larger the number of different angles, and the better the image definition. The larger the number of Voxels, the larger the number of different angles, and the better the image definition. So the more I have Voxels here, maybe more than 4, then the larger will be the number of different angles I will be viewing each of the Voxel via the X-ray beam. Okay, and the better the image definition of each of the Voxels. Now, the image on each Voxel has a particular intensity called pixel. Okay, meaning that every single Voxel in a section has its own unique intensity, which is called a pixel. So the question is, what are pixels? What are pixels? So let's quickly consider pixels. Well, pixels are measures. They are measure of X-ray. The measures of X-ray intensity transmitted through the Voxels along different directions. Okay, so there are measures of degree of X-ray intensity transmitted through the Voxel along different directions. How do I mean? From here, yeah, here I have my Voxels. Okay, when I have an X-ray from this right direction, okay, striking the O section, okay, what it simply means that it's also indirectly striking each of the Voxels. Okay, and every X-ray, okay, is it's incidented on the surface at a given intensity. Okay, so each of the x-ray has its intensity. Okay, so when this x-ray strikes on the Voxels, the intensity of the image formed in this Voxel here can never be the same to that of this, and can never be the same to that of this, as well as to that of this. Okay, so there's going to be a difference or variation in the intensity of the image on each of the Voxels. Okay, now from here, in fact, that is very practicable. That's why when you take a shot of yourself and you see your picture after taking your shot, you will notice that not all the parts of the picture is bright. Some parts are bright, some parts are dark, while some parts are fair. Okay, so it's not totally bright. The reason is because the intensity of light from the camera striking on you that's taking the piece, okay, is varying, okay, on you, which happens to be the section, okay, and it's varying from one Voxel to another Voxel of your picture. Okay, so the same thing is applicable here. When X-ray beam is released and it strikes on this section, the intensity on each of these Voxels will never be the same. Okay, one thing that needs to be noted is that the measure of each X-ray intensity or pixel on each Voxel, okay, on each Voxel is being denoted by using a unique number. What I mean is that to show the measure of X-ray intensity on this Voxel, or this one, or this, or this, a unique number is assigned to each Voxel, okay, to illustrate or to indicate that. Okay, so definitely that means each of my Voxel here ought to have their own pixel or X-ray intensity, since X-ray is striking on them. Okay, so this number could be of any magnitude, so it's not restricted to a particular value. So it could happen, it could be randomly, it could be of different values. Okay, so those are some of the things you need to know, and it's just something like this. Just like we have 1, so this one is showing that the intensity here is 1, and this one is showing that the intensity here is 7 candela. Then this one 2 candela. Then here I have 4 candela, which is the unit of intensity, which is that is candela. Okay, so these values you are seeing here simply represent the measure of X-ray intensity or pixel on each Voxels. On each Voxel. Okay, so right from here, we want to quickly look at development or construction of image using CT scanning. So how is image developed? Okay, most especially to give us a 3D image. Okay, so that's what we want to look at exactly, the development or construction of image using CT scanning. Number 1, image is developed by directing a beam of X-ray towards a section of a body at different angle while the detector reads the pixel intensity in the direction of each X-ray. Now what I mean is that image is only developed by directing a beam of x-rays towards a section, and that is done at different angles. Okay, now the detector function or duty is to read the pixel intensities. Okay, so from what we have here, each part have its own function. Okay, the x-ray has its own function, the detector has its own function. The x-ray only does the work of directing beam, the x-ray tube, of directing beam towards a section, different angle, while the detector only reads the pixel intensity, okay, or the x-ray intensity in the direction of each rail. Okay, that's one very big step in developing the image using CT scanning. Okay, let's see a case here. This is what I'm trying to say. Here I have the x-ray beam coming from the left side, that's striking on each of the Voxels in this place. Okay, on doing that, the detector reads the pixels on each of these Voxels. Okay, so what happened right here is simply that the detector reads what is here in this Voxel as 5, that is 4 plus 1, which is 5. Then it does the same thing here, 7 plus 2, which gives us 9. Okay, so that's what I'm saying, that the detector, which is this, only reads the pixels on the Voxels. Another one is that the x-ray tube and the detectors are rotated through angle 45 degrees for every change in direction. Okay, so the x-ray tube as well as the detectors are rotated through angle 45 degrees. Okay, so if that is the case, that means when this changes its direction, what it does is that it moves at an angle of 45 degrees away from its initial position. So let's assume that this object, of course, the x-ray beam always move in clockwise direction. So if the x-ray beam moves in this direction that I'm pointing to, okay, let me highlight it. Okay, if it moves in this direction, the direction of this arrow, okay, that is clockwise. Okay, so if that happens, what will be is that the x-ray beam will now be striking 2, 4, and 1. Okay, an example of that is this. Okay, this is what I'm saying exactly. Okay, now you can see the x-ray beam is no longer here, but rather here. The reason is because this is feeding this is feeding this, and this at the 4 and 7, while this is feeding 7. So the implication here is that when the x-ray beam rotates at an 45 degree, okay, the reading on the detector will also change. So the reading on the detector will not be as the same like when it was before. Okay, that is in respect to case 1. why this is case 2. Okay, now if it moves again for another 45 degree, so that will obviously be 90 degree to its initial position, okay, which is something like this. So only this section and this section, only this section and this section is recorded. That's by adding them up. So 4 plus 2 will be 6, 1 plus 7 will give us 8, and that is the third case in this situation. Okay, what if it moves again for another 45 degree? So that will be that will give us for this 45 to here, and that's 90 to here. So that will be 90 plus 145, which will give us the fourth case. So I will have something like this. I will have something like this when it moves for another 45 degree, and in this case, this will feed this, this will feed this. Okay, so as this feed this, it add up this one, and the reading is taken by the detector. Okay, so this is just the simple explanation of how the X-ray tube and detector moves when image is being taken. Okay, but at this point we want to quickly consider key points to note when developing image using CT scanning. Okay, so some of the key points are this. Number one, for every direction of the X-ray tube and detector, new Voxels are formed. So take note of that word, new Voxels are formed. It's very important. New Voxels are formed. That is for every direction of the X-ray tube and detectors. Then number two, is that the last Voxels generated after the X-ray tube and detector had rotated for 180 degree is the final pattern of the pixels of image form. Okay, I take that again. The last Voxels generated after the X-ray tube and detector had rotated for 180 degree, okay, is the final pattern of the pixels of image formed. Okay, so once you've noted that the last Voxels is being generated when X-ray tube and detector has rotated for angle angle that's less than 180. Sorry, in this case this ought to be a lesser value for 180. Okay, so let's use some of these steps with length to develop an image from a given Voxel of a section. So let's see how we can apply that. Okay, so a good one, we have the first case here when the X-ray is firstly directed to a section. Okay, just like this, I'm having the X-ray directed in this section. This is the original section with the first pixels and Voxels. Okay, meanwhile the X-ray can be directed from any side. It could be from here, it could be from here, it could be from the top, it It could even be from the right angle to the left, to the left. I've explained that before. And it could even be from the bottom. So the direction of the x-ray can start from anywhere. Okay, now when the x-ray strikes through this, I told you the first thing that happens, it add up the pixels in the two Voxels here, which is 5. Then the same thing is applicable here, which gives us 9. And what we obtained here is simply the detector reading. So it is referred to as detector reading. Okay, so the detector reading is then used to match each of the Voxels here. Okay, so if I do that, if I match the reading here to each of the Voxels here, what I simply mean by matching is that I'm replacing the values of pixels here by what I just got newly. Okay, so if I just do that, what I will end up with is a new set of Voxels. So 5 will be replacing 1, 5 will also be replacing 4. Then for the bottom part, 9 replace 7, then 9 replace 2. Okay, so with that, we are going to have another new Voxel in this place. That's why I said for every direction, there's always a new Voxel formed. Okay. Okay, so from here, what we got to do is to simply change the direction of the X-ray beam right there. Okay, and if we do that, I've said it, changing the direction of the X-ray beam will also result in changing the direction of the detector, because both of them moves at the same time. Okay, meanwhile, the detector reading here is referred to as the first set of detector reading. Okay, now if we go ahead and change the direction by 45 degrees, okay, so we'll end up having something like this, in case 2. So we'll be having this. So this is it. Now it has been changed from this direction to this direction. Okay, now in this case, this will be feeding this will be feeding this feeds this, while this feeds this. Okay, so the result from here is 1. Then the result from here is 7 plus 4, or 4 plus 7. That gives us 11. Okay, why this one gives us 2. Now the reading here is then recombined or merged, is merged to the new Voxel that was initially obtained at first. Okay, so if we combine it, what we get, if we combine it to the new Voxel we got the other time, then what we'll end up getting is this. How do we do that? It's very simple. So all I just got to do is to add this to this. Just look at the direction. It's very, very simple. If you feel you are going to get confused, you can use an arrow to indicate this is for this. Then this 11 is for the one in the middle. So it's serving two purposes here. It's serving 5 as well as serving 9. Then 2 here is for this. Okay, so 1 plus 5 gives us 6. 5 plus 11 gives us 16. 11 plus 9, that's 20. Okay, so having done that, I'll be having another new Voxel in this place, another new Voxels in this place. Okay, right from here, don't forget that the image formed, okay, in from one direction give us two dimensional image. That way you can see this just in 2D and not 3D. If it's in 3D, it ought to be in this form, but you can see I can only see just the face. I can't see any other part. The reason is because the image form is in 2D. Okay, since it's obtained just from one direction right here, so considering this in terms of its present direction. Okay, then if I go ahead and move, let's say the x-ray beam move again by 45 degree as well as the detector, so I'll be having this next in case 3. So I'll be having this exactly. This fits the whole of this fits the whole of this. That's okay. So this fits the, that's 1 plus 7 8, and this fits the, that's 4 plus 2 6. Then what I have here, the reading on my detector, is combined to the last new Voxel I obtained. Okay, just the most recent one I obtained the other time. So I'll just add up. So in this case now, it's gonna be 8 plus 6, that is 14. Then 8 plus 20, that's 28. 6 plus 16, that's 22. And 6 plus 11, that is 17. Okay, so what I have right there gives me the reading, the reading of a new Voxel, or you can say a new Voxel formed. Okay, so it gives you a new formed Voxel right here. Okay, so if I move the x-ray beam by another 45 degree, or if the as a x-ray beam move for another 45 degree, then I'll be having something like this, just as in case 4. So the beam will be coming from this direction, and each again this will feed this feeds this and this, while this feeds this. Okay, so following the usual procedure or the usual steps, okay, I will have my detector taking the reading for which is 1 plus 2, which is 3. Then this was feeding this, that's 4. This one's feeding this, that's 7. Now the reading right here is then combined to the last new Voxel I just obtained. Okay, then combine them together. So if I add it up together, to what I have here, then I'm combining this with it, which is the last Voxels I had before now. Okay, so what I'll be having is 4 plus 22, which is 26. 8 plus 14, that's 17. 8 plus 17, that's 20. Then 7 plus this gives me 35. Now what I have here is what is referred to as the final pixel of the image formed. Okay, and this can only be obtained, that is after we have got the fourth set of detector readings. Okay, that's why it is achievable. So for every single set of the detector reading, Don't forget, Voxels are formed, but the last Voxel form give us the pixel pattern of the object form, the pixel pattern of image of the object formed. Okay, so right from here we'll be able to see how to develop the image of a CT scan. So from here we want to see how to recover the original pattern of pixel. Okay, if you can remember, the original pattern of pixel we saw the other time was 4-1 then 7-2. Okay, but now I want to see how we can get it back from our final answer we got. Okay, so to do that we'll follow these rules. Number one, remove the background intensity or reading. Remove the background intensity or reading. Okay, background intensity or reading simply means the total of each set of detector or pixels readings. The total of each set of detector or pixels reading. So what do I mean by that? Each set of detector, if you add it up, or pixel reading, if you add it up, it will give you the background intensity. Okay, that is just very straightforward. I'm going to explain this using an example very soon. I'll do that. That is not hard to do, but meanwhile we can just do that. The reading from the detector we add when we first incident the X-ray on the section was 5 and 9. If you can remember, you can rewind, you can go back, you can back the video, okay, to check it up again. Alright, so it is 5 and 9. So all what you just need to do is to find the total. The total will be what? 14. Okay, so that 14 is what is regarded as background intensity. Okay, so we need to remove that background intensity. So what I will now be doing is to subtract it from the final Voxels I got. Okay, the new Voxel, the final one I got, I will just subtract from it. Now another important thing to do after doing the first one is to divide the result I get by 3 to allow for the duplication of views of the section. Okay, as the imaging is of the object is taken, there is duplication because there is a repetition. We repeated for another 3 times. Okay, and that could be that could happen over and over and over. Okay, so to give room for that duplication, to take care of that duplication, we need to divide by 3 since we repeated for another 3 measurement, for another 3. Okay, so we divide by 3 so that we can get a better picture, okay, of the new Voxel formed at the end of the day. So this is how it goes. The new Voxel that was formed was this. The new Voxel that was formed, the last one that was formed after finding the fourth set of detector reading, this was what we got as the new Voxel. So I said we remove background setting. Okay, so that means I'll be deducting the background setting from this. Okay, and that will be 26 minus 14. Okay, then 17 minus 14, then 20 minus 14, then 35 minus 14. Okay, so if that is done, then I'm going to have another new one again. So we have another new one right there. Okay, so that is 12. That is because I've subtracted 14 from each of these. That's why I'm having this. Alright, so the next one, okay, so the next thing is to divide each of the values here by 3 according to step number 2. So we divide the result by 3. So if I do that, this will give me 6, this will give me 1, this will give me 2, this will give me 7, and I will end up having this by that. So you can see it's giving me back the first Voxel I worked with. Okay, so that's one of the uniqueness. So this is just like a confirmation that what we did is correct. If we could not arrive back at this, it's an indication that okay, so it's an indication that we've not gotten the development very well. I mean the image construction very well. But if you can get back the original pixels, which is this, then it indicates that you really have done a serious work, a unique work in constructing the image. Okay, so from here we shall be looking at the principle of CT scanning. Based on what I've said so far, okay, we can conclude that there are principles guiding CT scanning, and I've mentioned some of these principles during the course of my explanation. So we're going to see those principles one by one. Number one of such is that CT scanning makes use of X-rays to take X-ray images. Okay, so that means X-rays are used to take X-ray images, unlike X-ray itself, X-ray scan itself, which only takes just one image. But CT scan use X-rays to take X-ray images. The second one, object is scanned in sections or slices and are repeated for many different slices, and that is what we have practically done under development or construction of image by CT scanning. Okay, so object is scanned in sections and are repeated for many different slices. Okay, the third principle, the scans are taken from different angles or direction, and I've talked about that is taken from angle 45 degrees. Okay, then the next one, scales scans of many sections are combined and processed. Scans of many sections are combined and processed. Okay, so the combination of the image of many sections, the scans of many, which is image of many sections, are combined and then processed. Then the next one is that the combinations gives a 3D image of the whole structure. I've explained that before, that when you combine the image of each sections together, what we're going to end up getting is a 3D three-dimensional image. Then the next one, the 3D image can be rotated, as I've said that as well. Then a computer is highly needed to store and process huge quantity of data. Okay, that's why I said the other day that computer is very important. Okay, then the next one, the computer also help to vary the brightness and contrast of the image, and that is just perfectly true. So those are some of the couple usefulness of computer, okay, in CT scanning. So this is one of the reasons why a CT scan will not work properly or will not give a better result if computer is absent. Okay, because there will not be anywhere to store and process huge quantity of data, and there won't be anybody to adjust the brightness and contrast of the image. So everything can be perfectly done by the computer. So at this point we shall come to the end of our class. Let's quickly consider some questions. You can try to lay your hands on each of these questions. The first question is this: briefly explain the principles of CT scanning. And you can see the mark, 6 marks was allocated to this. So you are asked to explain that, meaning just highlight, okay, the principles of CT scanning. Then there's a second question, so you can pause the video to have a look at the question very well. The second question continues here. Okay, then the next question is this. Then the next question is this. Then we have the next question, which is this. Okay, then I have another new question starting from here. The question continues right here. The question continues right here. And here we come to the end of the lesson. So you can check up the next video on other topics for a better understanding. Do have a lovely day. Looking forward to see you in this channel again. Bye for now.